Okay, go for it.
All right. All right. So as I'm going to do this like we did yesterday, so I'm just going to share some of the slides of the tutorial, and I think I'll just briefly go over some of the key points that I think are important. And if you have questions, if you watched the movie, or even if you didn't, I'm really happy to answer. So let me share this. Can you see this?
Yes.
Okay. Um, so this tutorial, it really went over two aspects of learning. So one which was more of a biological forms, STDP, Hebbian learning, but then raising some of the issues with biological learning, which is that it's not really derived from task requirements, but rather from neuroscience observation. That's not a problem in itself, but if you're trying to build a technology that works well, it's also informative to start from the task requirements, such as it's done in machine learning, and relate this possibly to the neuroscience experiments. And so what I'm showing here is actually in some resemblance to EPROP, as we saw earlier today. So it's really starting with the description of the spiky neural network, describing this in a computational graph. And it turns out that computational graph has a lot of similarities with what people use in artificial recurrent neural networks. And so we can apply the same ideas, the same tools, and the same mathematical theory to derive a learning rule that is specifically tailored to that neural model and that objective function, or the loss function. And so this is the where we also get these so-called three-factor rules that have this external components, the error, this sensitivity of the neuron to spiking, as well as this eligibility term here. And so putting these all together, we can actually build train spiky neural networks through gradient descent. And there's been actually a number of work that has used this, including from the lab of Terry Sinowski, and also Friedemann Zenke, which partly this work has been done in collaboration with. So there's been quite a number of work out there. So what really this gives us is a mathematical framework for understanding how to relate learning rules to neural models. So later, I go to the details of what are the specific challenges here. So some of the challenges are that if we're doing gradient descent, then we need those functions to be differentiable. And one way to overcome this is to use smooth functions in the optimization. Another problem is the spatial credit assignment. So we need to somehow backpropagate the errors. That's the job of backpropagation. But we can also achieve this using local errors, which is in some resemblance to also what Wolfgang was explaining earlier today. And finally, also temporal credit assignment. And here we can relate the learning rule that we're using to backprop through time, but more importantly, to the flip side of backprop through time, which is called real-time recurrent learning. It turns out that these two things are actually computing exactly the same product of Jacobians, except that they're doing in different modes. And we just recently realized that actually our implementation was not doing one or the other, but it's actually doing something called a mixed approach that mixes backprop through time within the time step, which then is not actually through time, it's just backprop, with this forward method called real-time recurrent learning. So this is by itself a new way of implementing spiking neural networks and auto differentiation now that really is really efficient for implementation of spiking neurons. So that's just for the introduction of the tutorial. And if you have any questions, please ask them.
So Emre, this is still a time-stepped approach, right? So that means that you're still
Yes,
considering
so this is, absolutely, this is a time-stepped approach, but it's time-stepped because we're implementing these on GPUs. There is, in fact, a continuous version of all of this. And, Walter Zen and Mihai Petrovici are actually working on those continuous time versions as well, and they're quite similar.
I see, okay. Let's see now. I think there's a question on the chat. So hold on a second. I see something. It says, Emre, I think somewhere in your tutorial you mentioned that surrogate gradients refer to the derivatives of a smooth version of a spike. How is this different from other approaches of gradient-based learning in SNNs, which low-pass filter the spikes and then do backproponent?
Well, yeah, so it's very, I think it's very similar. I'm not sure which work you're referring to, but it's if you back propagate through the activation function, that's where you're going to have the problem. So what you can do is that, you know, if you have a single layer network, you don't necessarily have to back propagate through the nonlinearity, right? So you can just take the output of the previous layer and just basically calculate the gradients without going through the derivative of the activation function. But as soon as you do that, then in this gradient-based approach, you have to somehow take that activation function into account. Or you can ignore it at some cost and precision.
Yep. So I think the question is really about like what I mean. I'm not familiar completely with this literature. I don't really follow it. But do you remember the paper from Junhang Lee?
I do, yeah.
The guy from Samsung, yeah. So he basically low pass filtered. It's all wrapped up in a quite lovely theory, which I never quite understood. But basically, it amounted to low pass filtering the input to the neuron, the membrane potential, and also the output spike rate. So it's kind of, you needed to be spiking quite hard.
As soon as, Toby, I know that worked really well. So as soon as you go into spike rates, you don't really have this problem anymore, right? Because then what you're doing is that you're replacing that spiking nonlinearity with the rate nonlinearity. And in some ways, what we're doing is not so different, except that, I mean, there's still some work to be done. So what does that smooth function really mean, right? So is that like it may be somehow related to the rates input-output rate transduction now.
Hey, would you mind just repeating in the context of that, what you mean by our approach? Just repeat again what you say, what's different about our approach versus the...
Okay. So there are, you see, actually I went quickly through this, but there are three problems here. One, which is the nonlinearity. That's problem number one. And that's, I'd say, you know, we can overcome it fairly well. So that's done. 2 and 3 are the problems that this mixed approach is solving. It's orthogonal to how we're treating the nonlinear activation. Does that make sense? You see here the sigma here?
Yeah.
And so so this normally going from U to S, right? So how is S computed? It's a theta, a step function of the membrane potential. So the arrow would be forward there. What I'm showing here is a gradient graph. And you see in the backward graph, I have this sigma, which refers here to, you know, it could be a sigmoid function or a piecewise linear function. So it's only used for optimization. And that sigmoid function, you know, we could also choose something that's somehow related to the rate function, but I don't want to go too much into details there.
Okay. Maybe, are there other questions maybe from the community? So let's just see from the Slack.
There's another question, Emre. So a couple of questions on the STDP implementation. Could you elaborate a bit on how you went from the standard form of STDP to the online STDP? Is there a difference in the information needed between the two formulations? That's the first question. And I'll ask the second question afterwards.
Let me already answer that one. Yeah, I see the feed here.
You see it now, right? Okay.
So let's see. Did I? Oh, you mean this one? Okay. Let's see. Can I easily explain this? So in the end, what you want is that the weight change be proportional to these two curves, right? The curves here, and you make certain assumptions when you move to the online form that these curves are going to be exponential, okay, and that so that's the main assumption here, and so you can show that these weight updates basically will follow the same updates as here.
Let me
there's no easy way of explaining this. I think you just have to go over the math here. I did this in some past, but I can't remember the details, so I can spit them out here. Right
I will now put the question directly on the slide, right? So you cannot avoid them. Whoops.
Oh wow, cool.
No, but it disappeared. Okay, do you see it there?
I see it there, but is that on the?
It's not good. It's lousy.
I think I prefer the.
Yeah, right.
Erase that.
You mentioned SCP depends on the location of the synapse relative to the sound. Oh yes, so this is work also of from Wolfram Gerstner. He has a really nice paper on this. So in fact, on these SCDP models and others, feel free to chime in here. It turns out that the further you go away from the axon hillock, basically where the spike is generated, the more rate-like your learning rule becomes. So in that paper, 2002 paper, they explain how you can have these both kind of generalized Hebb rule versus the generalized STDP rule, and that's depending on where you are on the neuron, you might have one more than the other, or a mix of the two. So that's exactly the case.
Nice. So, and then there's another question, from Matthew.
Right. So about how does this relate to super spike? So I mentioned that we did this work also in collaboration with Friedemann, Zenke, who actually is the author of Super Spike. So it's the same thing.
And then the next question.
Why do you need P and Q then replace U? Okay, so this is actually a nice trick
What question is that?
Oh,
yeah,
I'm
maybe
sorry.
you should read the question.
So it says, in your tutorial notebook on local errors, why exactly do you need P and Q then replace U, the code in lift and slate? So this is a trick that what you can do is that you can replace your integrated fire neuron dynamical equations with that of the spike response model. The spike response model is an easy way to explain it is that instead of having a differential equation, it's an equation of the integral over the past. So when you write it in this way, it gives you this really familiar kind of artificial neuron form where you end up with something like, I can actually write on my screen here. You end up with something like U is equal to W times P plus V times Q. So these would be, oh, I'm sorry, in this formulation, there's actually no V times Q, so there's only a WP. Plus a reset term here. So this is the formulation that you get with the one type of spike response model. And the cool thing is that when you write it this way, you see, if you plug this in an auto differentiation library, it's going to treat P as if it were inputs, and it's just going to differentiate this as you would differentiate a normal neural network. And so this is how we can achieve the implementation of the mixed mode without actually doing forward mode automatic differentiation, which PyTorch doesn't natively support. What I just said in the last few words might be overly complicated here, but I'm glad to explain more.
Your mic is getting really soft for some reason. I don't know why.
Okay.
Yeah,
is that better?
Better,
okay.
much better.
Okay.
So there's another question.
There's another question.
If you have recurrent connection, SCP will not work, right? Because you are going to have secondary. No, actually, SCP will still work, right? It's a phenomenological model that just depends on the input and output spikes. So you can basically also have neurons in the same network feeding into each other. The rule still applies. Same goes actually for the rules that we're implementing. I mean, it can easily apply to recurrent neurons. So
I think that's it. Okay, any other questions out there?
Yeah, keep the questions coming. I mean, it's great. This is a chance to ask. Maybe show your slide sorter view. If you have the top view of all the slides, maybe somebody is impelled to ask a question about a particular slide. If you have the overview.
Slide sorter view.
Yeah.
I'm actually on.
There's another question that popped up, Emre.
Oh, okay. How can you use local errors for practical oh, so that's object recognition is the easiest one here. So local errors are, well, let me just explain for the audience what local errors are. Um, um, so I like to explain this with the game of Chinese whispers. Like this is back propagation, right? So the entry point is here, and the input is here, the output is here, and as you go forward and backward, or I'd say the point of Chinese whispers is that the message is sent from the input to the output and distorted. And so the output becomes slightly different than the input. And then what we can do as the supervisor is tell that person on the end, okay, here's the correct answer. And that gets propagated backwards to this separate network. So that's what backprop does. And so one way to overcome the problems related to this, and we know the problems of backprop is that we need these symmetric weights, we need these two-phased learning, and we need to, or our learning depends on the future rewards, as we saw in Wolfgang's talk. So one way to overcome this is to define these local errors. And this is quite similar also to how Wolfgang was mentioning that we replace these total derivatives with partial derivatives. So that's a similar idea. And so what we do here for image classification, what you can do is Hisham Mostafa, who was a postdoc in Gert's lab, really nicely showed that if you define these local classifiers to these local loss functions to be classifiers that are only backpropagate through to that local layer, then this works very well, surprisingly well. In fact, better than feedback alignment if you're familiar with that. So that works well for object recognition. And Wolfgang really nicely showed that you can also evolve these different loss functions for different problems as well, and do in this way kind of fast learning. So I see another question. By the way, if I didn't answer your question well, just so feel free to continue asking your questions. So I see Shavika asking, in forward AD, weights are updated online without propagating error backwards. That's correct. Then how do we calculate gradients for weight update as we do? Oh, well, that's, so I can refer you to one really nice article by our colleague Christina Savin, who really explains this real-time recurrent learning in a more, I mean, it's a very old rule. So it was 1989 by Williams. And it just hasn't been used because of the scaling properties. And so that paper explains this well, but I'll try to give you the idea here. So as you backpropagate, or as you calculate the gradients of some loss function L, what you're doing is actually, and I think Daniel Bedau actually made this comment yesterday, what you're doing is that you're calculating vector Jacobian products. So it's just a bunch of matrices that you have, and the order in which you calculate, you do these products is going to determine whether you do backprop through time or real-time recurrent learning. And so in the end, you end up with the same gradient in one way or the other. And so basically the mixed way is just that you're free in a product of Jacobians to do products, to put those parentheses actually in wherever you want and do, for example, portions of these matrices are computed in a forward fashion, others are done in a backward fashion. So in the end, you still get the same gradients, and when you apply them, so you end up with the same thing. So that answers the question. But otherwise, once I'm done here, I'll send you the reference for that really nice article from Christina Savin. There's another question there. Is this truly computational graphs? Are there efforts to implement this? Oh, yes. So actually, yes. So are there efforts to implement this in neuromorphic hardware or transfer these models to existing platforms? Actually, we do have an implementation in Loihi of this. where we actually also do these few shot learning, because we can, we understand the equivalence between backprop through time and real-time recurrent learning in this mixed mode. We can also mix these two approaches. And so what we do here is that we actually pre-train a network on a known data set, and then we can train the neuromorphic hardware on these new data sets and on these new gestures. And this learning rule that we're implementing on Louis is basically applying this these surrogate gradients. So this is just like also Wolfgang mentioned, these are local learning rules where all the information you need is going to be located at the synapse or at the neuron. And so this is a very good candidate for implementation in neuromorphic hardware as well.
And by the way, I think you should see the AI cast. By the way, if anybody doesn't know this, AI cast 2020 is the Artificial Intelligence Circuit and Systems Conference. The papers are all online now on IEEE Explore. I don't know if they're open access or not, but anyway, all the papers from this conference are online, and I think it's the surrogate gradient paper that you guys put in that conference. So look at that paper, right? I think isn't that explained there?
Yeah, it is explained. Yeah, so this is there's a new version of this actually that's on archive right now. Well, you'll recognize this figure. Yeah.
Yeah, you can just post that on the Slack, the archive later.
Great.
Any other questions? Oh, there it is. Okay, somebody, yeah.
I see another question on the Zoom chat. While implementing.
Mugrank posted that nicely.
Oh,
okay.
Oh, great. Okay, so we have a newer version that we just posted like last week, and I'll also send that into the to the Slack later. So there was some problems with the old rule. Yeah.
Nice.
I will also, yes, Yuan Zheng, I'll also send the papers for the SCP and recurrent networks. Yeah. And I do see another question on the chat here saying, while implementing this DBS work, is the accuracy drop on the classes between right arm clock? Oh, no, the accuracies that we have here are not class specific. So the example that I'm showing in this histogram, if that's what you're referring to, this is actually just one instance. In fact, the instance of this particular input. Okay. And so it turns out that this was a right-hand wave, which actually you can't really see from the picture alone. But yeah, so this is just I think some output spikes, total number of output spikes during that presentation.
By the way, everybody who's posting your questions onto Zoom, we're going to turn off the chat in Zoom, just join the Slack group and post your questions there. It's not that hard.
I think it's all right, Toby. I mean, we can copy it over to Slack.
No, it's okay. It's not all right. I mean, I think we should have one place. Anyway, we'll talk about it later.
Yes, right. I mean, we can leave the chat on. You can always copy it for those who cannot manage Slack. Okay.
So the question was, there's a question, right?
There was a question, yeah. So I answered it saying that why is the accuracy drop on the right arm clockwise and anti-clockwise? So that's not what you're seeing here. So what you're seeing in this histogram is just the readout, actually, the readout for one sample.
Okay. Emre, how do you combine these local predictors to have the general outputs?
Well, it's up to you. So what Hesham did, so Hesham is a collaborator here also. So you can actually look at just the output layer here, right? So the last layer at Y3. In fact, that's how we used, the errors were reported from this classifier here. These first two classifiers are only used to generate a better representation to allow the subsequent layers to learn to perform better. And this is the case. So if you look at the accuracy of Y1, Y2, Y3, you'll see that they increase as you go deeper.
Thank you.
And Emre, do you have some idea of why you should learn with a lower error with the call?
You mean by by having these local losses. And
Yes, yes,
this
correct.
is a hand wavy, I mean, it's still very hand wavy for the moment. And basically the nice way that Hesham was describing this was so these connections here, I can actually annotate here. So you see these connections here. Oh, what? Somehow it didn't. Oh, there you go. So these connections here. Oh, gosh, why is this? Okay, there you go. See these connections here? These ones are not trained, so they're actually random. And we, similar to this idea of the mixed mode, right? So we actually back propagate here. All this is happening in one time step, so there's no major credit assignment problem. And we discussed this in the paper. And what this does is that you learn some representation at this point here that is a little bit more disentangled. That helps the next layer learn from that representation. Yeah, so that's the intuition, and you.
I see. It doesn't depend on how you initialize the weights, or does it?
No, it doesn't seem to. It doesn't seem to. I mean, initialization is important, just like in any deep neural network, but it's not something that was problematic here. Nogai is asking, so the classifiers of the earlier layers are only for weight updates? That's correct. Yes. So all these classifiers, we actually call them like pseudo losses, are only there to help the learning problem. They're not, so you may or may not use them, right? So in practice, what we did is we trained a much larger network here. This was actually 6 layers. And after the 3rd layer, we didn't see any improvement. And so we just chopped it off to 3. So that's another way to do it. You can basically train the whole layer and just chop it off wherever, things perform well. Toby, so you say, how does,
you oh, sorry, go ahead.
Let me just answer Toby's question. How does all this relate to self-supervised learning? Oh, yeah. So I would say that they're different things. I think self-supervised learning is very important here because in practice, if you look at this example that I was showing with the Loihi, at the end here. So you see, actually, my student, you don't see his right hand because he's actually pressing on the keyboard while he's training this. So the labels were provided externally. I think this is completely compatible with.
Emre, move your mic up again.
Oh gosh, yeah. So I was saying this is it's compatible with the self-supervised approach in that if you plug in these basically not classifiers, then just regressors at the intermediate levels, and try to learn another signal provided by the network, I think this might help. And we haven't done this yet, but this has just always been on our plate. But yeah, I think it relates, but the fact that we're using local losses doesn't directly relate to self-supervised learning, if that makes sense. Hector has a question there. Can you please comment on performance differences between? Okay, so the performance difference between conversions from normal dense networks to spiking networks. So Terry Sanofsky actually gave also an explanation on this. The benefits you get from training directly with spikes are huge. So you can really train smaller networks along with the spiking dynamics. Generally, normal dense networks, you train them, well, it depends if you train a recurrent network or a spiking neural network. If you train a non-recurrent versus a recurrent, if you train a non-recurrent network and move these to spikes, I think that's not the right approach for many reasons. Just because you're losing the one of the really important features of neuromorphic computing and biology, which is that it's a dynamical system. It's it has its own dynamics and temporal and temporal features. And if you don't use that, it's just gone to waste. That's why it's important to really take those dynamics into account, and you can do this by training recurrent neural networks. There's also some work in converting recurrent neural networks to spiking networks. I think Shichi, isn't one of your students doing that?
Yeah, the Bodo.
Yeah, but yeah. So that is, that's a potentially more interesting approach, but the time scales at which you'll be learning are going to be different, right? Recurrent neural networks, they're generally are trained within a few time steps. In our case, if we would have done this with backprop through time, this would be hundreds of time steps to really take into account those fine temporal scales. Yeah, so that's, but I'm happy to discuss more about this.
Okay, so Emre, I think we do another maybe couple of questions, then we wrap it up so that we can bring in the other guys.
Okay, sure. So sure, I'm just going on, but feel free to stop me. Yeah. There's another question that are the classifiers specific to single layers to provide locality? That's correct. They are defined in the same way, but the local losses are only used, they only backpropagate up to here and no further, so that we remain local. Did you try to scale this up to a complicated task?
But what do you use, Emre, for the reference, for the target for these local clusters?
Oh, the true labels, the true labels. So this is what Hisham used in his
Okay,
work,
true labels. Okay,
yeah.
okay. Mm-hmm. Thanks.
So Alex has a question. Did you try to scale this up to a complicated task? Do you have a reference or some results on how many parameters? So I don't know what you mean by complicated task.
I think a bigger data set. A bigger data set, I mean.
So the problem, okay, so this is a good question. The problem that we're having is not that we're limited. In fact, these are very easy to train. They take a couple of hours. They take only a fraction of the GPU memory. And we can build much larger networks, right? So easily 1 million neurons fits on a single GPU along with the training. The problem is the data set, right? So which data set actually makes sense to plug in here?
Hello?
Emre, are you there? I had an answer.
Yeah.
I had a question for you.
I think Emre is stuck.
I think we should go to the other talk, Shichi.
Yeah, right. So
Yes,
I'm gonna stop this recording, okay? And then we'll go to the informal discussion. So hold on a second.